Chapter 8 focuses on hypothesis testing. We're going to combine the first two sections together and spread it out over a few different videos. To start, let's compare hypothesis tests to confidence intervals. In a confidence interval, we estimated the value of a population parameter based on a sample. In other words, we took a sample, we found either a proportion or a mean from that sample, and we used that sample to estimate what's the actual population parameter, the mean of the whole population or the proportion for the whole population based on that sample. This is called an inferential method. We're using a sample to make some kind of judgment about a population. For example, in a sample of 200 M&Ms, 58 are blue. What proportion of all M&Ms are blue? Based on the sample, we would come up with a proportion range of 22.7% to 35.3%. That's with 95% confidence. In a hypothesis test, instead of creating an estimate about the population, we're going to answer a question about that population parameter based on that same sample. So does 58 blue M&Ms out of a sample of 200 provide evidence that blue M&Ms are manufactured at a rate greater than 20%? Notice that we're answering a question here. Is the proportion of blue M&Ms greater than 20% compared to confidence intervals where we take our sample and we're using that sample to estimate what is the proportion of blue M&Ms? So we're always going to start off with an initial hypothesis when we're doing a hypothesis test, and this is called the null hypothesis. It's denoted with this symbol, H sub O. In this case, our null hypothesis is that the proportion of blue M&Ms is 20%, P equals 0.2. There's always a second hypothesis. This one's called the alternative hypothesis, and this is the one that's true if the null hypothesis is not true. Okay? And this is always what we're trying to prove. We want to prove that the proportion of blue M&Ms is greater than 20%. Null hypothesis always has an equal sign, and the alternative always has some kind of statement of inequality. So maybe it's a not equal to sign, greater than sign, or less than sign. All right, we wouldn't want this to be like a greater than or equal to or a less than or equal to. And we wouldn't want this up here to be a less than or a greater than. Okay, so we always have an equal to sign up here and an inequality, one of these three signs for the alternative. When we do a hypothesis test, we're gathering evidence against the null hypothesis. We're trying to prove this wrong. And if we're able to prove that wrong, we're left with the alternative. So we've proved the alternative true. Now that tends to be kind of confusing for students, so I want you to think of a hypothesis test like a jury trial. When we're conducting a jury trial, we have a defendant. We always start off by assuming the defendant is innocent and collecting proof about their guilt. Okay, we want to prove their guilt beyond the reasonable doubt. If we're able to do that, we reject their innocence and we conclude that they're guilty. Okay, that's basically how a hypothesis works. In a hypothesis test, we start off with our null hypothesis. We assume it's true. Okay, we collect proof in the form of a sample in order to reject that null hypothesis. And if we're able to reject the null hypothesis, we conclude that the alternative hypothesis is true. Right? We want enough proof that convinces us beyond a reasonable doubt that the null hypothesis is incorrect, and therefore the alternative hypothesis is the correct one. Just like in a jury trial, we're trying to prove their guilt beyond their reasonable doubt. We reject their innocence beyond a reasonable doubt. So let's get back to this question at hand. Is there evidence to support that blue M&Ms are manufactured at a rate greater than 20% based on a sample where 58 out of 200 M&Ms are blue? So our hypotheses, which we mentioned on the previous slide. Null hypothesis is that 20% of M&Ms are blue, nothing to see here. Alternative is that this sample provides evidence that more than 20% of M&Ms are blue. First thing we want to do is find the standard deviation. This standard deviation should look familiar. It's the one that we were using for confidence intervals, with the exception that the P and the Q don't have hats on them. Okay, so we're not using the P hat from the sample, and instead we're using the P from our null hypothesis. Okay, the reason we're using this P is because we believe that this is true until we're convinced that it's not true. All right, so we're going to put 0.2 for the P, 0.8, which is 1 minus 0.2 for the Q, and this 200 is the sample size from our sample up here. Okay, we get a standard deviation of 0.0283. Now the p-hat from our sample, 58 out of 200, is 0.29. Okay, is this an unusual result? Okay, let's look at a normal curve. So if this is true, and it's right in the center of our normal curve, would it be weird to get 29% blue M&Ms? Okay, now this is just a z-score problem. Okay, is this unusually far from our mean, the middle of our curve, based on this standard deviation? Okay, so z-score is our data value minus the mean divided by our standard deviation. We get a z-score of 3.18, and we can use this to look up a probability. Okay, the probability of this occurring, based on this being true, is 0.0007. Now this probability that we just found, this 0.0007, is called a p-value. And the p-value is a conditional probability. It's the probability of seeing the observed statistic, meaning the 58 out of 200 M&Ms, if the null hypothesis is true and the actual proportion of blue M&Ms is 20%. It's really unlikely that 58 out of 200 M&Ms would be blue if only 20% of all M&Ms were blue. That leads us to believe that the actual percentage of M&Ms that are blue is more than 20%. Because of that, we're going to reject the null hypothesis. This is evidence to us, beyond a reasonable doubt, that the proportion of blue M&Ms is not the 20% that the null hypothesis stated, and instead the alternative hypothesis is true. The proportion of blue M&Ms is greater than 20%. Now, we want our p-value to be small, and we define small as below 5%. The chance of getting 29% blue M&Ms in a sample of 200 is so small, 0.007, that we can reject the null hypothesis and conclude that the proportion of blue M&Ms is actually above 20%. When the p-value isn't small, it's telling us that the results we're seeing aren't unusual and the data is consistent with the null hypothesis. Let's say, for example, we found 42 blue M&Ms out of 200. That's 21%. That's not unusual at all compared to the 20% we're expecting. This would have a p-value of 0.3618. This is right around one-third being 0.333. Okay, so in other words, if we were to take a whole bunch of samples of 200 M&Ms, we would expect to see 42 or more blue M&Ms about 1 out of every 3 times. Okay, this is not enough evidence for us to be convinced beyond a reasonable doubt that the proportion of blue M&Ms is greater than 20%, and we would fail to reject the null hypothesis. So here are our key equations. We have our null hypothesis. This is just assigning our proportion value to some number. Okay, and that's the number we use in our standard deviation. We don't use the sample value like we did in confidence intervals. When we get to our z-score, we take that sample, that's the p-hat, and we subtract the null hypothesis value. Okay, that gets divided by our standard deviation, and that gives us a z-score, which we use to find the p-value. Let's take a look at this example. Here we have a report in Men's Health magazine stating that 39% of cardiologists take vitamin E supplements. There's a researcher who wants to see if this is still true, so they take a sample of 100 cardiologists and find that 36 say yes, they take these vitamin E supplements. Does this provide evidence that less than 39% of cardiologists take the supplements? Part A, define the parameter. This is just having us define what we're actually testing with our hypothesis. So in this problem, we're testing the true proportion of cardiologists who take the vitamin E supplements. We're assigning it the variable P because it's a proportion. Write the hypotheses. Our null hypothesis is that 39% of these cardiologists take the supplements. This is about all cardiologists, the whole population. The alternative is that our sample, which is this part of the problem, is a bit lower, and it's suggesting that now that number is no longer 39% and it's actually less than 39% of all cardiologists. Part C, find the standard deviation, and we want to use this null hypothesis value in our standard deviation. Okay, standard deviation is PQ over N, using 0.39 as the P and the corresponding Q. So 0.39 times 0.61 over the sample size, 100. Gives us a standard deviation of 0.0488. Okay, next up, find the z-score. So here's our normal curve. Okay, we're assuming that this 39% is true. We always assume that this null hypothesis is actually correct until we find enough evidence to convince us otherwise. Would it be unusual to get 36%? 36 out of 100 is where that 36% comes from. Is it unusual to see that amount or less? We're going to go out to the end of the curve based on this standard deviation. Okay, so a z-score 0.36 minus that mean value of 0.39 divide by the standard deviation we found in part C gives us this z-score. Look that up in your z table. We get a p-value of 0.2676. Example 2, we have a dietitian that saw a survey saying that 55% of adults skip breakfast at least 3 days a week. The dietitian thinks this number is too high. They take a sample of 80 adults and find that 50% of those 80 say they skip breakfast. Define the parameter. P equals the true proportion of adults who do not eat breakfast at least 3 times a week. Hypothesis. Okay, P equals 55%. It's still that 55%. Alternative, it mentions up here, the dietitian thinks that this number is too high. So in other words, they think that it's less than 55%. That's our alternative hypothesis. Standard deviation. Use this null hypothesis value, 0.55, okay, to find that standard deviation. Sample size is 80. We get a standard deviation of 0.0556. All that goes into finding the z-score. Null hypothesis is in the center of our curve. Is it unusual to get that 50% or less based on this standard deviation? Okay, so 0.5 minus 0.55 divided by that standard deviation. Z-score is negative 0.9, p-value of 0.1841. Last example, a Harris poll found that 35% of people say they drink a caffeinated beverage to combat midday drowsiness. A sample finds that 19 out of 48 people agree with that statement. Does this survey suggest that the true proportion is different than 35%? This is a key word here, different from. Okay, it's not saying it's greater than or less than, it's saying is it different from. Define the parameter. P is going to equal the true proportion of people who drink caffeine to combat midday drowsiness. All right, so different comes into play in our hypotheses. So null hypothesis is that P equals 0.35. The alternative is that it doesn't equal 0.35. It's different from 0.35. Standard deviation, plug everything in, we get a standard deviation of 0.0688. Is it unusual to see this amount of people out of 48? So let's figure out what percentage that is. Okay, so we get a p-hat of 0.396. Is that an unusual percentage based on a null hypothesis of 0.35? Okay, so we find a z-score for that, and we get a z-score of 0.67. Okay, we want to find from 0.396 out to the curve. Look that up. Okay, now remember, when we look up a z-score, it's always telling us area to the left. So we have to do 1 minus. When we do 1 minus this, we get 0.2514. Okay, but since this is a not equal to hypothesis test, it's not a greater than, it's not a less than. Okay, this would be a greater than hypothesis. When it's saying not equal to, it's really both of those together, which means we're going to take this tail, that right tail, and we're going to mirror it on the other side. So this 0.214 that we got on the right side, we also have over here. Okay, so we're just going to double that 0.2514. So we do 2 times that, and that gives us our actual p-value of 0.5028.